Hi, Dan here, Scooter Magazine. We're going to do another video today, this time on the relationship of ignition and compression with jetting and exhausts. This applies to both Vespa and Lambretta scooters, and so I'll just run through some of the fundamentals that I used to use when setting up engines at the garage. Individually and collectively, the subjects of ignition and compression and jetting can be quite complicated if you want them to be. I quite enjoy getting down into the depths of all the different nuances on it, but for the purpose of your average rally-going scooterist who just wants to set his scooter up sort of safely, but in a good way that gives it the best combination of safety and performance, then there are a few sort of rules of thumb that you can utilise without going into all the depths of the science behind every individual nuance. So if we start with the ignition timing, if you don't know, the ignition timing on Vespa and Lambretta, it's usually set via the stator plate and the flywheel. This is an old points ignition, but most modern scooters now will be using an electronic ignition, and it's basically through the adjustment of that. I will do a separate video which is a practical how-to on setting both Vespa and Lambretta ignition timing, and then the marking of the points and the strobing of that. Back in the day, you would often see on some of the 200cc engines from the big manufacturers, you would see ignition timing not suggestions in the owner's handbook of 21 to 23 degrees, and that was standard back then. You had 4-star leaded fuels which could cope with that sort of thing, but as unleaded petrol came to the fore, and then amounts of ethanol in the petrol and one thing and another, we've really had to scale back the expectations of what sort of ignition timings you can run. And you saw people peel back from 23 to 21, 21 to 19. And when I was setting up scooters in the garage, I would pretty much set the largest majority, unless there was something unusual going on, I would set the largest majority of the engines up on 17 degrees. Sometimes I would go as low as 16 on specific scooters, and perhaps occasionally as high as 18. But for the largest percentage of scooters I set up, it was 17 degrees static ignition timing. Now, somebody asked me an interesting question the other day, and they said, "What's your opinion on the various types of variable ignition that you can now get, and whether that be the Kepper, the Augusto, Vespatronic, MTech, whatever." There's a variety of variatronics. There's a variety of different units which you can now use in order to give you a sort of variable amount of advance and retard on your ignition curve. And my opinion on those is that they're great. They really are very, very useful items, but I specifically like to use them in quite limited circumstances. And the way that I would approach this is, what is the overall purpose? When you're playing with one of these units, what's your goal? And my goal was really to look at it and say, what's the setup of your scooter? What is your kit, ignition and carb? And then let's have a look how that translates into your power curve. And if, for example, you were running something like a Vespa or Lambretta 200cc in a fairly sort of basic trim, and you had a Clubman pipe on there which was quite torquey from the low down, and a nice sort of touring carb, 26-28mm or whatever, you often already had a tremendous amount of nice low down power. You generally, with those setups, aren't lacking in torque and low down grunt. Okay? So in those instances, I saw absolutely no benefit to using an advanced retard ignition unit. There were no losses down the bottom end that really needed bridging. And even moving on from the Clubmans, if you had a decent touring pipe, and for example something like the TSR Evo or the NK Rally, they were expansion chambers which had great low down power potential. So there wasn't really anything missing down the bottom end between tick over and you sort of coming onto the pipe for you to then worry about bridging the gap. However, if you'd gone for a pipe which was perhaps more power orientated and had a higher peak curve, you often find with those sorts of pipes that there is a gap down the bottom end, so between tick over and the pipe coming on song, and you might find on a France Speed race pipe, for example, it really doesn't come onto its starting its efficient curve at around 5,250 RPM, and then it will climb in power and efficiency until it reaches its peak at around 8,250 or thereabouts, depending what tune you've done. But that gap between tick over and it coming onto the pipe at 5,250, you could really perhaps then think, that's a bit lacking, I'd like to bridge that gap a bit or improve that loss in whatever way possible. And at that point I would say, right, let's have a look at a variable ignition unit. And there are many on the market, but ones which had various different settings were quite useful if they had a few different maps in. And then you could say, right, well, between tick over and 5,000, I'm going to move from the 17 degree static, and I'm going to use this little unit to add in some degrees of ignition, and I might then set the tick over at around 23, and then it would come back gradually as the revs went up, so that when you started coming out pipe at say 5,500, you were then coming back to the safe static 17, where then the power curve would kick in and that would take the motor forward. And maybe even at the top end I might just add in another little couple of degrees, so that once it hit peak power at 8,250 I might even bring it back to from 17 to 16 or even sometimes 15. So using it in that way to bridge a gap briefly down the bottom end, and also remembering, if you've watched my jetting videos, to fuel that curve, then you can burn that extra fuel, bridge the gap with some extra degrees of ignition, bring the bottom end up nicely to meet the 5,250 curve, and then go up onto the pipe and then just bring it back safely at the top. For the purposes like that, those little ignition units and variable advance boxes are invaluable. But if you've got a touring setup with a touring pipe, touring kit, touring cab, touring chip, whatever, and you're not lacking down the bottom end, you don't need one. You really don't need one, and it just becomes an added complication for the average rally-going, road-going scooterist who isn't bothered about pushing everything to the depths of, you know, the heightened performance, and it's just an unnecessary complication. Outside of those, as I say, static ignitions of around 17 degrees. 17 degrees was my overall favourite, and on a couple of the Vespas, like the T5, I might come down to 16, and on some, maybe the Vespa P200 in its stock trim, go to 18. But outside of that, once you put a Molossi kit on it, I'd bring it back to 17, and anything that goes outside of, you know, standard territory, it would be 17 was my favourite, broadest used, most widely used static ignition curve. Now, static degree fixed timing. Now, for whatever reason, some people can get a bit uppity about how scooters are set up and who's right and who's wrong. And I don't see it as who's right and who's wrong. I just see it as what's your way of doing things and does it work for you? Well, some people would say, I've been running 19 degrees for years now and never had a problem. Great, look, if it works for you, fine. I'm not here to convince you otherwise. Other people would even go a step further and say, I'm still running 21 degrees on mine, and been doing that for however many years, no problems. Great, again, if it works for you, fine. But invariably, what I would find on nearly all of those types of motors, if they ever came into the garage, was that the reason those people were getting away with running 19, 20, 21 degrees of ignition timing was that then they'd had to grossly overcompensate on the reduction of compression and the richening of jetting in order to allow the motor to run that kind of ignition timing. That's what I would find on the motors that came into my garage. And on occasion I'd heard story of people going to certain dyno outlets where they'd gone in to have a carb tune, and the carburetor had been tuned and it was initially rich on arrival and been leaned off to a good safe spot, but then gone away, and this guy had hauled a piston on the way home. His initial reaction was, well, clearly the dyno operator had leaned off my carb too much. And I don't know for sure, but my suggestion there was that no, he didn't lean off your carb too much. He probably took your carb out of the overly rich settings you got it on, put it on a perfectly, adequate and safe level of jetting. But when he done that, he hadn't checked out your ignition timing and checked to figure out that what he was putting your carb on was going to work with the ignition timing you'd got, and the normal jetting had exposed the weakness on the advanced timing of 19, 20, 21 degrees, and then caused problems. So the way I would do things is that I would say, if you peel the ignition timing back just 2 or 3 degrees, bring it back to 17, to that nice safe spot, any losses that you believe you will incur in power by doing that will be far outweighed, or at least equalled, but in my opinion far outweighed, by then the ability to put the compression in a better area and bring the rich jetting down to a more normal area. And with you not having to then mask the problem, you've got an engine which is running cooler, more efficient and more power. So once you get that balance of 17 degrees or thereabouts, 16 in some and 18 in others, but there or thereabouts 17 degrees, and you can then bring your jetting down into the correct area and put your compression up, you've got quite a good balance of settings there. Now, in terms of the compression, for those who don't know, in your cylinder head on your Vespa or Lambretta scooter, you're going to have a combustion chamber, and outside of that combustion chamber, but within this bowl area, there is a band of metal where your piston comes up, and at top dead centre comes incredibly close to that band of metal which surrounds the internal combustion chamber. The inner bowl, and when that piston comes up and meets the squish band, its job is to squish the gases out from the outer edges of the piston and head into a central combustion bowl. And the reason it does that is to try and keep the running temperatures down on the outer edges of the piston, where they might otherwise increase due to pre-ignition and or detonation. Basically unburnt gases at the edges there, causing heat problems. So if that mixture is squashed into a bowl in the centre, it can be utilised better for power. So the size of that bowl and a few other measurements in coordination with the kit you're running, the height of your exhaust port and some other things, will give you a compression ratio as the piston comes up and compresses and squishes the gases into that bowl. You may or may not have a head gasket in there, which if you do, that needs to be taken into consideration into the measurement of your compression ratio. Okay, I will at some point do a video for a practical of how to measure your compression ratio and how to calculate it, and I'll also put a link in this video to a great article that was done in the magazine which basically shows you how to do it. So I'll put a link in this video to show you another web article on our site to show you how to do it, and I'll also later do a video practical. But so the compression ratio is essentially the gas is squashed up into the cylinder head with or without a head gasket taken into consideration. Now, the traditional ratios that I would like to see road going and rally going scooters use is a uncorrected 9 to 10. 9 to 1 and 10 to 1, but anywhere between those two is a good uncorrected compression ratio in my opinion. Anything lower than that and you can start to unnecessarily reduce power, and as I say, usually people who've got too much ignition degrees would be doing that, but if you've got your ignitions down at 17 or 16, then you can run decent compression, and up to sort of 10 to 1 is a good uncorrected figure. Anything beyond that, and you're starting to get into sort of performance areas and closer boundaries of tolerances, and it's unnecessary on a rally going, road going scooter. That would equate in depending what kit you're running and the height of the exhaust port and all the rest of it, around 5.5 corrected as your lowest performance-based efficiency figure, and up to, and it's debatable, but I preferred a maximum ceiling on a rally going, road going sort of a corrected of 6.3 to 1. Some people say 6.1, 6.2. I found up to 6.3 would work. Strangely enough, I was looking at some figures of current manufacturers, kit manufacturers at the moment, and there's a very well-known, reputable, good reputation kit manufacturer at the moment putting out a little 200cc small block Lambretta kit, and their own figures stated in their fitting handbook tell you that the compression ratio of that little kit, which is a very, very popular touring kit, is, I'm going off memory here, but I think it's 9, on a 60mm crank, it's a 9.77 uncorrected compression ratio, and the corrected compression ratio is actually 6.6. And so that's a current kit manufacturer. And I have built dozens of those kits, and although that corrected compression ratio is just a tad higher than I actually normally like to see, they've obviously, figured out that it works well for them, and I never had any problems with it. So there is a little bit of wiggle room there, but for safety reasons, I say 6.3 is a safe upper limit of corrected compression ratio for rally-going, road-going scooterists. In terms of the Squish band, the band of metal which surrounds your combustion bowl, which the piston will come up to, a reasonable way, a rule of thumb for calculating the required squish, there's a couple of ways. A popular one is 2% of stroke. Another popular way is 1% of rod length. And invariably, whether you're going from a little T5 with a short stroke motor and a shorter rod, or up to a Lambretta with a 62mm crank and a 116 or a 120 rod or whatever, if you measure them, they'll invariably fall somewhere between around 1.1 to 1.3 mil squish. Anything less than 1.1, and you're starting to get into the realms of consideration that eventually when the motor heats up, or after a few miles when the bearings start to wear and there's extra play in them, or if you over rev and get some con rod stretch or whatever, but at some point the motor starts to run too hot, thermal expansion or extra play in the bearings, and the piston will start to kiss the head, and you do not want that. So any lower than 1.1, you're starting to get into sort of race motor territory and sort of smaller margins of error. Anything above 1.3 and you're starting to go beyond where the Squish Gap will, it starts to then function less efficiently as a Squish Gap. And they say that once you go over 1.5, you're starting to really minimise the effects continually as you go big. I've measured engines, they've come in, they've had Squish Gaps of 2.3 mil. And effectively at that point, it's just not working as a Squish Gap. It's not helping the way it should do to quench the outer edges of the piston, prevent the detonation in the pre-ignition, and of course you're getting power losses because those outer edges of gases don't burn as efficiently as the ones in the central combustion bowl. So any gases, mixture of oil and petrol and air that are squashed up in there, if they're in a big fat squish area at 2.3 mil, they're not being used as efficiently for power as if you close that gap up to say 1.3 and get all those extra gases pushed into the combustion bowl. So if you have a big fat squish on your scooter, then you're probably losing power, and in some cases probably running hotter than you would do if you close up the Squish Gap and run a tighter gap. And 1.1 to 1.3 I think is a really, really great spot. And on most sort of 57mm Vespas 200cc's and 58mm Lambrettas or 60mm Lambrettas, 1.2 to 1.25 is absolutely bang on the money for a rally going, road going scooterist. You've got good clearance for safety but nice and tight for performance and cooling. I'll do a video on that, but basically at the very least you want to be using the simple method of putting some solder down the plug to touch the back of the cylinder wall and just turning the scooter over to get that, you know, one measurement. The preferred way of doing it is with the head off and doing a sort of 4-point check to make sure there's no unevenness in the head or the cylinder or any of the engine build setup components, because you don't want squish of 1.2 on one side but 0.9 on the other, and then, you know, that's when you're going to get problems with the piston touching the head. So in terms of your squish, 1.1 to 1.3, calculate as 1% of rod or 2% of stroke. Your corrected compression ratios, I like lower limits, lower thresholds of 5.5 corrected up to an upper limit of 6.3, although I have seen some current production kits run very well on 6.6, although that is the exception rather than the rule in my opinion, and they're only that high because of their very low exhaust port duration, and that would be an uncorrected head of between 9 to 1 and 10 to 1. One thing I will say, I've seen people who have got compression ratios which are too high, they need to lower them, and I see it all the time on Facebook, and people say, oh, pop a thicker head gasket in. It's like a cheats way of increasing the head volume. Now, one, I don't think that will necessarily increase it enough if you've got a problem with pinking or detonation, so I don't think it's the right way, you know, the best way to go about it anyway. But further than that, you're going to enlarge your squish to something which is, you know, if you've got a 1.4mm squish, it's on the borderline of where you want it anyway, and then you go and stick a thicker head gasket in to reduce the compression ratio, and you enlarge your squish now to like 2.4. It's the wrong way to do it. You're just going to end up losing performance, probably a hotter running engine, and you know, it's the wrong way to do it. If you need to lower your compression, then you need to increase the size of the bowl in the head, and the only way to do that is take it off and either if you've got a lathe, you probably know how to do this, you don't need to be watching this video, so presumably you haven't got a lathe and you need to send it to somebody who has, and any of the well-known big name scooter shops in the UK usually do their own heads, or usually there's a guy very close to where most people live who's a really clever guy with a lathe and he'll do it for you. But you know, I'll do a separate video on getting that all set up. And then jetting, as I say, I've done the video on jetting, but basically anybody who's running advanced ignition times of 19, 20, 21 and those realms, they're usually running very inefficient and reduced compression ratios to cope, and then usually vastly rich over jetted carbs to compensate. So at the top end you've got these three components: timing, compression, incorporating squish, and your jetting. At the other end of the scooter you've got a fourth item which needs to be taken into consideration, and that's your exhaust pipe. Now, even if you have no interest in performance, you should know that the exhaust pipe is probably the single most influential factor of your engine's characteristics, whether that be performance based or touring based. And you can take an engine which has been otherwise vastly overported and put a really great touring pipe on it and tame it immensely. So when you hear people saying, oh, I like this kit because it's a Revy kit, or that kit because it's a touring kit, you can really change the characteristics of any kit with the right exhaust. Okay, so bear that in mind when you're making your choice of what exhaust to get. The other thing to bear in mind, and this is the most important bit for the safety of setting up an engine, is the stinger. And on this expansion chamber, it's easily seen, it's this last tube here in the exhaust pipe, and they usually just sit in here a little bit. The length of that stinger has some quite important effects also, but the most influential factor certainly for most of the Vespa and Lambretta scooters you see, where they're buying off-the-shelf exhaust pipes, length of stinger isn't usually a problem on most of those. It's the diameter, and by that I mean the internal. This is a removable stinger, most of them aren't, but it's the internal diameter of this tube, and it's calculated as a percentage when people are making the exhaust pipes of the header pipe, and the CC is going to be running on. But But if you just want a rule of thumb, you can look at what motor you're running, and there are some rough guidelines that you can use instead of measuring header pipes and calculating percentages and all the rest of it. What the Stinger does is it acts as a bleed valve for pressure coming from the engine, from the cylinder within the pipe. And if there's too much pressure, you will get too much heat. Now, if you increase the pressure, you can get more performance, and that's what a lot of people do. If they want to get higher peak powers, they can reduce the diameter of the stinger or play with the length of the stinger, or both. And what you would see is sometimes naughty pipe manufacturers trying to get the edge over other pipe manufacturers, and the way they might do it, if their pipes were both vastly similar, is just perhaps reduce the internal diameter of the stinger a little. You'll then see a better power curve, peak power, everybody goes and buys the pipe. If you're not looking at the internal diameter of the stinger of the pipe and calculating it to your size of engine, then that could lead to problems. And the rough rule of thumb that I like to use is on a 125 to 175 cc engine, a stinger of no less than 22 mil on the smaller cc end, the 125, and up to sort of 24 mil on the 175 cc end. Once you move up into the 200 cc category, I don't like to see a stinger or internal diameter of below 25 mil. Okay, if you go above that, yeah, you'll see bigger power, but you will see more pressure, more heat, and probably hole a piston very quickly. And once you go up to the sort of 250cc bracket, I don't like to see anything less than a 26 mil stinger. That's me personally. 25 to 26 mil. On some occasions, it's actually, depending what the overall package of the engine is, the power output and the BMEP of it, it can be necessary to even go bigger than a 26 mil on a 250cc engine. 26, 27s wouldn't be unusual in certain applications. But for the largest rally-going, road-going scooterists who are doing sort of trying to build safe engines, don't get a stinger internal diameter of smaller than 25 mil on a 200cc engine. The only other thing I want to say is, and I will cover this more in depth when I do the practical videos of how to set up the ignition timing and how to measure compression ratios. In regards to the ignition timing, if you're going to set up ignition timing, never ever trust the existing timing marks that have been left there either by somebody else or even by the manufacturer. In my opinion, you have to find top dead center, calculate where your 17 degree static is, set your stator plate and flywheel up to match that, and then strobe it. That's the bit. You need to strobe it. And until you've strobed it, you cannot be 100% certain as to what your ignition is doing. I have seen some scooters which are supposed to have static ignition, and there's been a slight variance on the electrical setup of the CDI and the stator and one thing and another. And they actually have inbuilt, without knowing it, areas of advance and retard, and you could see something set at 17 and then you rev it. I weirdly saw a number of scooters, you would rev them, and when you they were set at 17, they strobed at tick over at 17 and you revved them, and they would actually go up to 19 or 20. As much as 2 or 3 degrees of advance. Or sometimes I saw it go the other way, and I didn't mind then. If I saw something and it was ticking over at 18 and then you revved it and it came back to 17 or 16, I didn't worry so much about that because that's safer. But if it's going in the wrong direction, and I have seen it on a number of scooters, you've got problems with poor quality or mismatched components. So the only way to know that your scooter is ticking over and revving at the right ignition timing is to strobe it. So make sure you strobe it no matter what. So that's all for this. 17 degrees is a good there or thereabouts, as low as 16 on some setups and as high as 18 on others, but 17 is my favourite. 9 to 1 to 10 to 1 on uncorrected. Or as low as 5.5 or as high as 6.3 on corrected. I have seen some running on 6.6. They seem to be doing okay, so there is wiggle room there, but it's not what my recommendation would be. And then jetting to suit. And if you get those 3 things set up, check out the stinger diameter. You're probably going far further than 90% of the people who we encountered as customers who came to our scooter garage, because most people can get a little bit bogged down and swamped with the technical aspects of these things, and so they sort of step back from them and just think, well, if my scooter's running okay, I'll leave it. And there's a lot to be said for that. If it ain't broke, don't fix it. But sooner or later, if you run into a problem with a dodgy batch of fuel or perhaps an air leak, and you've got no room for error or margin of error, then things, if they're on the edge, they can go pop. But certainly, lost power through, excessive ignition timings, and reduced compressio and rich jetting was a very common one. So, hope you've enjoyed this video. I'd love to hear your comments on how you set your engine up and what experiences you've got. As I say, my way is just the way I do things. It works for me. I'm not saying it's the only way or the best way, but it's certainly with a good track record with it. So hope you enjoyed the video. See you on the next one.